Bismillahirrahmanirrahim. My name is Rana Ali Hassan, student ID 230090670001 from the Department of BS Chemistry. Today's topic is acetaldehyde. Following points we will learn in this presentation. First, introduction of acetaldehyde. Second, history of acetaldehyde. Structure of acetaldehyde. Properties of acetaldehyde. Formation of acetaldehyde. Selective reduction of CO2 acetaldehyde. Application of acetaldehyde. Uses of acetaldehyde and references. Introduction. What is acetaldehyde? Acetaldehyde, IUPAC name, ethanol is an organic chemical compound with a formula CH3CHO, sometimes abbreviated as MeCHO. It is a colorless liquid or gas or boiling near room temperature. It is one of the most important aldehydes occurring widely in nature and being produced on a large scale in industry. Acetaldehyde occurs naturally in coffee, bread, ripe fruit, and is produced by plant. It is also produced by partial oxidation of ethanol by liver enzyme alcohol dehydrogenase and is a contributing cause of hangover alcohol consumption. Pathways of exposure include air, water, land, or groundwater, as well as drink or smoke. Consumption of disulfide inhibits acetaldehyde dehydrogenase enzyme responsible for metabolism of acetaldehyde, thereby causing it to build up in the body. The International Agency of Research on Carcinogen has listed acetaldehyde as a group 1 carcinogen, and it is one of the most frequently found toxin with cancer. Then we talk about history of acetaldehyde. So acetaldehyde is discovered in 1774 when Carl Williamson synthesized acetaldehyde. However, its structure was not completely understood at that time and named aldehyde to its chemical group, which is derived from the Latin phrase. Following their discovery, aldehyde triggered the growth of modern perfume industry and also in agriculture and manufacturing industry. In addition, aldehyde from the environmental source cells are also endogenously produced aldehyde as signaling molecules. Aldehyde are highly reactive within cell and can form attacks leading to DNA damage and alter protein activities. Understanding the fact that reactive aldehyde alone the cell is of great importance in humans as these leading to cancer, diabetes, cardiovascular, and neurological disease. Intracellular aldehyde can be neutralized by aldehyde metabolism enzyme, including those from aldehyde dehydrogenase superfamily. In particular, the importance of aldehyde dehydrogenase 2 in aldehyde metabolism has come to the forefront of precision health, more so in the past decade. This is because an inactive ALDS2 genetic variant is present for nearly 8% of the world population that limits aldehyde metabolism. With aldehyde exposure, the inactive aldehyde 2 variant leads to a greater risk of cancer and cardiovascular diseases. In effort to gather research across the world involved in the aldehyde research, and then we talk about highlights of the biomolecules special issues. For this special issue, the 9 original article and 2 review article on detoxicity metabolism represent research from laboratories that span across 4 continents, including 7 countries. Aldehydes are toxic to cells that can cause DNA damage and protein and the formation of special tissues identifies the continued need to examine aldehyde toxicity and metabolism directly caused by alcohol in consumption in addition to aldehyde generated from source other than alcohol. When consuming alcohol, the key enzyme responsible for converting acetaldehyde to acetic acid is aldehyde dehydrogenase 2. Furthermore, 516 million people worldwide are intolerant to alcohol due to an inactive genetic variant in aldehyde dehydrogenase 2. For heterozygotes, aldehyde 212 this leads to an 40 to 60% reduction in aldehyde 2 enzymatic activity. How long ago did the genetic variant appear in humans? To test this question, Lee Linus L. identified that aldehyde 2 genetic variant originated 7,935 years ago using the long haplotype analysis for residents from Keelung, Taiwan, and from China. Furthermore, when examining 750,000 genomes worldwide with respect to alcohol use disorder identification test score, the aldehyde 2 variant is the only genetic variant influencing the audit score, leading to less alcohol use. In a separate study within the special issue, Yi Yang Chen et al. Made the aldehyde 1B2 and aldehyde 2 genetic variants can affect alcohol metabolism. 60 male 25-year-old were given alcohol challenge followed by measuring blood ethanol acetaldehyde level using gas chromatography and high-performance liquid chromatography. Also, the blood ethanol concentration was unchanged by aldehyde and aldehyde 2 variant acetaldehyde accumulation occurred dose dependently after alcohol consumption in participants with an aldehyde 2 variant. This finding suggests that aldehyde 2 variant, unlike aldehyde 1B, directly correlated with acetaldehyde accumulation. Taken together, these studies suggest that regardless of ADH1B genetic polymorphism, the psychological effects of alcohol are directly linked to inefficient metabolism of acetaldehyde by the aldehyde 2 genetic variant for those of East Asian descent. In a separate study by Nassai et al. Examined in rodents how the aldehyde 2 genetic variant can impact bone loss with dental bacteria. Concomitantly with alcohol by quantifying the proliferation and mineralization of human osteoblasts in vitro, it was observed that aldehyde-2 knockdown transferred osteoblasts grew more slowly compared to the control transfected osteoblasts. Furthermore, when wild-type and aldehyde-2 knock-in mice were injected with a purified lipopolysaccharide from the pig inguinalis and given 10% alcohol for 6 weeks, the bone defects in the aldehyde-2 knock-in mice were significantly increased by 30% compared to wild-type aldehyde-2 mice. This suggests that aldehyde-2 genetic variant increase the risk of dental bone loss when exposed to alcohol. Oral bacteria in the studies Imposel reported accidentally associated with alcohol-induced com cell syndrome, suggesting alcohol-dependent acetaldehyde metabolism prevent cancer associated with alcohol consumption. Alcohol consumption also impacts the cardiovascular system, and previous studies have identified association between alcohol consumption and genetic atrial fibrillation. In this regard, Hung et al. Examine East Asian impact of daily alcohol consumption carrying the aldehyde 2 variant of left atrial electromechanical parameters, including the peer intervals, left atrial volume, empty infection volume index, and carriers of aldehyde 2 variant with modest alcohol consumption demonstrated more impaired left atrial electromechanical parameters and higher clinical risk to develop alcohol-associated atrial fibrillation related to those. Aldehyde 2 star consortium. In order to raise awareness regarding how genetics may influence aldehyde metabolism, the inaugural aldehyde 2 star consortium started with an agreement between Stanford University and Taipei Medical University, Taiwan, spearheaded by Chi Hong Yen and Derry Rosen, with great support by Yun Chen to host the event and Taipei Medical University. The initial meeting was focused on sharing tools, technology, and scientific expertise between Stanford University and Taiwan as we together research together who studied topic involved aldehyde too. Our consortium continued until the COVID-19 pandemic with the fifth annual aldehyde 2 star meeting hosted by Kaohsiung Medical University in Kaohsiung, Taiwan. And for this meeting, over 200 people registered for a 2-day event representing 6 different countries. And this is a reference from which this article is taken. And then the we talk about structure of acetaldehyde. So acetaldehyde has a chemical formula CH3COH and 44.053 gram meter per liter is the molar mass. Acetaldehyde molecule contain normal functional group of aldehyde HCl with double bond of O linked to the methyl group, making it the second most simple aldehyde after formaldehyde. And then we talk about the physical properties of acetaldehyde. Acetaldehyde is a white substance with a very strong scent. Furthermore, its boiling point is 22 degrees Celsius and melting point is negative 123 degrees Celsius and has density of 0.784 gram meter per liter. Acetaldehyde, on the other hand, is soluble in miscible water, ethanol, benzene, acetone, and toluene. It is also mildly soluble in chloroform. Then we talk about chemical properties of acetaldehyde. Acetaldehyde has chemical electricity comparable to formaldehyde. It is used as an electrophile precursor in organic synthesis. Condensation reaction provide intermediates such as pentathiol, which can be utilized in chemical synthesis. It may also be used to make hydroxyethyl derivatives by reaction with Grignard region. Acetaldehyde is a building block used in the production of heterocyclic compounds such as amines and phenadiene. Methods for manufacturing of acetaldehyde. First of all, oxidation of ethylene. It is the main method which oxidation by the Becker process, which involves oxidation of ethylene using a copper system of palladium. In this process, ethylene oxidation uses raw material where ethylene is obtained from petrochemical industry. Oxygen to form air. Becker, Chemi, and process developing the first direct liquid phase oxidation of ethylene in 1957 to 1959. The catalyst with an aqueous solution. In the 1894, the main reaction is given process. There are two variation for the production of acetaldehyde oxidation of ethylene. A single stage manufacture of acetaldehyde is by direct oxidation of ethylene in a gaseous phase in the presence of platinum chloride and water. Ethylene is oxidized in a bubble column reactor containing an aqueous solution of with oxygen in cyclic process at 400 Kelvin. Under pressure of 3 bar, the gas current leave the reactor steam containing steam, acetaldehyde, ethylene, and small amount of oxygen. And then this material is cooled in a condenser to about 80 to 130 degrees Celsius. The condensate formed thereby substantially consisting of water, small amount of acetaldehyde is taken generally recycled to the reactor, and also of some copper oxalate and high molecular byproducts are also likewise formed remain persistent in a catalyst solution where the unreacted starting amount leave the reactor. Next, the portion is released from the pressure, whereby the dissolved low boiling points such as acetaldehyde, ethylene, and carbon dioxide flash are removed, and then where it is heated to temperature of 160 to 180 degrees Celsius. The gases then leave and the product is generally cooled further to about 30 to 80 degrees Celsius in a heat exchange. Then the product which is washed out from the gas current in a scrubber. The residual gas, mainly consisting of ethylene, oxygen, carbon dioxide, inert gas, is cycled to reactor after having removed one of the gas. And after having added fresh ethylene, conveyed to two-stage distillation process. In this process, the low boiling point and the dissolved gas such as ethylene and carbon dioxide are obtained as overheated. The bottom product is passed to a second distillation step where pure acetaldehyde is obtained, as the overhead product and a fraction contain only formaldehyde is withdrawn as steam side stream in the two-stage process. Ethylene oxygen second stage, ethylene oxygen react liquid phase, the production of acetyl oxidation of ethylene, oxidation of ethanol, desired reaction is given, thermodynamics and kinematics of reaction. The overall reaction is exothermic and the temperature in the reactor is 550 degrees Celsius. This is why cooling is required before the absorption process. Catalyst used silver catalyst used for process description. The process is very similar to a silver process that is used to produce formaldehyde. A big difference is that for acetaldehyde, the distillation is columns are required while the formaldehyde only one is required since the process of oxidation. Air is required. Ethanol is first heated, then mixed with air in a saturator. The saturated stream will contain ethanol saturated in air. After that stream is overheated in order for it to be able to react in the reactor. After that, the heart of process, the reactor ethanol saturated stream enter the reaction, undergo two main reaction, mainly other reaction that produce some byproduct. The catalyst used is silver. The product steam is very hot, therefore the heat of the steam can be used to produce steam from water using a heat exchanger. Further long cooling is required to prepare the steam to enter the absorber should be maintained at 2 degrees Celsius. The bottom steam full absorber is sent to distillation column to separate acetaldehyde. From ethyl alcohol, acetaldehyde is produced commercially by the catalytic oxidation of ethyl alcohol passing alcohol vapor and preheated air over silver catalyst at 4800 degrees Celsius carried oxidation with a multi-tubular reactor conservation of 74 to 80% per pass can be obtained while the generating steam to be used else in the process. Acetaldehyde also produced commercially by dehydrogenation of ethyl alcohol. Temperature 280 to 3500 Celsius process. The following section will describe a silver process for acetaldehyde production from ethanol. Air and preheated ethanol goes into a saturator. The air leaving is saturated with ethanol around heated before entering the reactor. The main reaction take place and the byproducts are formed according to the reaction. Ethanol is mixed with air and passed over zero catalyst at 560 degrees Celsius in the reactor. The high temperature gas from the outlet of oxidizer is cooled and condensed then sent to scrubber to absorb acetaldehyde and unconverted ethanol. Nitrogen, hydrogen, methane, carbon monoxide, and carbon dioxide gas and another inert gas is discharged from The tower, the diluted acetaldehyde solution at the bottom scrubber, which contains acetaldehyde, alcohol, acetic acid, and water, is sent to distillation tower after heating. The gas phase fraction from the tower top after condensation is partially collected, which is 99% acetaldehyde, and most portion is reflexed back. There are also some impurities in the present person. The impurities in the bottom stream are sent to waste treatment. The distillate consists of 85% base solution of ethanol, which is then recycled back. Unsaturated hydrocarbon acetyl is formed as a co-product at vapor phase oxidation of saturated hydrocarbons such as butane mixture containing butane with air or in high yield. Oxygen oxidation of butane yield acetaldehyde is another process to form acetaldehyde. Formaldehyde methanol is a non-mixed solvent. This is the historic interest. Unlike the acetylene route, it has almost no chance to be used as a major process. From synthesis gas, a rhodium catalyzed process capable of converting synthesis gas directly into acetaldehyde in a single step was voted in 1974. The process comprises passing of 50% rhodium, 5% rhodium on SiO2 at 300 degrees Celsius and 20 atm pressure. Principal co-products are acetaldehyde 24%, acetic acid 20%, and ethanol and 16%. In the year 1980 and beyond, if there is a sufficient degree of coal gasification, the interest in the use of synthesis gas as a raw material for acetaldehyde production will increase. And then we talk about selective reduction of carbon oxide to acetaldehyde with copper Ag electrocatalyst. Electrochemical CO2 reduction is a promising approach to store renewable energy in the form of energy-dense fuels for sustainable synthesis of feedstock chemicals. Copper is currently the only electron material that has own significant of CO2 or activity toward multi-carbon fuels and chemicals, albeit with a widely divergent selectivity toward our 16 different products. Previous studies on copper electrodes have shown that CO reduction is the rate limiting step in the transformation of CO2 to further reduce product. In addition, providing important mechanistic insight for CO2 or direct electrochemical CO reduction can also serve as a sequential route for reducing into multi-carbon products when utilized in tandem with existing technologies that can efficiently generate CO from CO2. Thus, there are motivation to understand how the guide CO are respective to the desired product. Number of strategies have been developed to address the challenges of steering CO2 or selectively by modifying either the intrinsic or extrinsic properties of the electrolytic system. Example of successful control city properties to guide selective include modifying electrochemical surface composition, particle size, and roughness factors. Similarly, researchers have demonstrated that the intrinsic factors such as electropotential, electrolyte quotient, identify concentration, and molecular additives significantly influence reactivity for CO2 or COR. Although all of these studies have provided tremendous insight on how to get selectively to broad product groups such as C2 plus oxygenates and hydrocarbons, controlling the reaction selectively toward a specific product is still a major fundamental challenge. In this work, we leverage insight from the aforementioned strategies that control the extrinsic properties of electrocatalytic system with the aim of steering the selectivity of COR toward a single C2 plus oxidate to modify the intrinsic electrocatalytic properties of CO electrode with implemented on AG galvanic stage process as previously indicated that OAG bimetallic electrocatalyst enhances selectivity towards C2 plus oxygenate by suppressing the competing hydrogen evolution reaction. In addition, alkaline pH conditions were used for CO based on previous study that shows energy efficiency and selectivity to C2 plus oxygenate can be improved by governing this splitting property around the electrocatalyst. As hypotheses were found that combined approach of tracking intrinsic and extrinsic properties lead to an efficient electrolytic system that exhibit a Fardic efficiency of 50% for COR to acetaldehyde with hydrogen as the only other major product. Remarkably, over 90% of the CO that goes to the formation of acetaldehyde. Density functional theory calculation explains the high selectivity of acetaldehyde as the Ag atoms on copper surface lower the intrinsic activity for acetaldehyde reduction by introducing electronic effects that weaken the binding energy of its key reduction intermediate. The fundamental insight from this work provide general design strategies that can be utilized for discovery and development of efficient the electrolytic system. Following other results and the discussion about the experiment, also metallic AgL copper are thermodynamically immiscible at room temperature. Previous work had demonstrated that copper-silver surface alloy with dilute silver content can be formed by galvanic exchange of copper with silver using a silver ion precursor solution. It has been shown that the activity of CO2R to multi-carbon products observed over COU-based alloy increases extremely with the surface composition of CU, suggesting that neighboring copper atomic ensembles are required for efficient CC coupling. Therefore, a low silver surface content is preferred in order to maintain a surface rich with copper active site. Inspired by these previous studies, copper silver electrode was prepared by immersing pre-polished polycrystalline copper foils into a dilute silver nitrate solution. The product distribution for the copper-silver electrode indicates that acetaldehyde is formed in significant quantity at all electrochemical potentials. The highest selectivity towards the acetaldehyde is observed at minus 0.536 volt. The reversible hydrogen electrode with a Faradic efficiency of Ca 50% that accounts for 90% of total CO reduction partial current. Comparing the CO testing result of copper versus copper silver clearly has a high selectivity to a single liquid product acetylene in contrast to pure copper, which forms seven different products at this potential, including five different liquid phase species and another two different gas phase products. While the overall selectivity for all COR products remain consistently 50% for copper silver within range of electrode potential used for testing. Where a clearly potential balance change in the product distribution, for example, at more negative electrode potential, selected toward acetaldehyde decreases concomitantly with an increase in selected toward ethylene, eventually ethanol. Then we talk about difference. The difference in the activity depend upon electrode potential indicates that acetaldehyde and ethylene may go through different pathways after CO dimerization, which is consistent with the previous theoretical work focused on understanding mechanics of Ce2 product formation. Previous studies have shown that the cascading homogeneous reaction can close on CO2 or CO product distribution. Control HNMR experiment indicate that Sanizaro's type disproportion is not a significant homogeneous reaction pathways in 0.1 molar KOH. Testing natural transformation directly and electrochemical process under the condition we use for CUV experiment. Instead, these HNMR experiments support a previous conclusion that acetaldehyde can be polymerized by a homogeneous reaction in alkaline condition, including product quantification for COR. Notably, these reactions appear to be reversible as acetaldehyde can be recovered by simply neutralizing the electrolyte in 0.1 molar HCl. A decrease in overall CO activity is likely to due to silver galvanic exchange occurring mainly on the step and under-coordinated copper surface, which are mostly instinctively active servo COR. To further explore the influence of catalyst comparison, we use previously implemented physical vapor deposition method to prepare a broad range of copper-silver thin film composition with interface visibility. Unlike previous CO2 studies that showed clear dependence of partial activities on the copper-silver composition, similar activities and the selectives were observed for the most all of the bimetallic thin films. This result suggests that the types and the proportion of surface active sites are similar for all of these catalysts under alkaline condition. Surface-sensitive operando probes could provide further evidence for surface restructuring and guide the future design of new catalysts. To determine why copper is silver selective was used to acetaldehyde, we conducted acetaldehyde reduction experiment with activities of copper and copper silver for producing ethanol. The result demonstrated that copper silver is significantly less active than copper for acetaldehyde reduction, explaining its high selectivity for acetaldehyde. To rationalize the expression in acetaldehyde reduction, the burning energy of the key reaction intermediate CH3CH2O was examined using DFT. This exercise was calculated to be the most favorable site for Ag doping. Based on the previous studies, Ag doping reduces the H binding energy of copper carbonating suppression in hydrogen production that is observed experimentally. Similarly, in the most stable absorption sites of CH3, CH2 surface are calculated to be H side as shown in the free energy diagram that given above. The diagram shows that potential limiting step for reduction is the first proton electron transfer step from CH3, CH2 where the H is replaced by the silver and the binding energy of CH3, CH2 is weakened by 0.09 electron volt. When the copper atom is close to the absorption side, is replaced by the silver, and the binding of CH3 is weakened by 0.31 electron volt. In both cases, there is substituting higher thermodynamic energy value for conversion of CH3, CH2, CH3, CH4. Thus, silver compression into Cu mitigates acetaldehyde reduction, thus greatly improving the rate of production, corroborating the experimental result. However, this improvement in product selectivity comes at the cost of decreased overall CR activity since the CuH sites are most intrinsically active or COR taken together. Results suggest that manipulating the binding energy of COR reaction intermediates by controlling the catalyst composition, which is a viable strategy to improve the selectivity for COR toward valuable products. To fully find and rationalize the high COR selectivity to acetaldehyde on copper silver. It was also important to understand how silver influence the bioproduction between the acetaldehyde ethanol. The acetaldehyde pathway. Also, a number of DOT studies have led to observational reaction mechanism and a putative intermediate common to the bifurcation point between these pathways yet to be determined either theoretically or experimentally. Identifying a putative intermediate will aid in understanding how control COR and COR certain single multi-carbon products such as copper silver for COR. With the above knowledge in hand, we then aim to explore the impact of electrode surface area on COR selectivity. It has been previously demonstrated that electron roughness factor can steer COR selectivity toward the multi-carbon oxygenates on pure copper catalyst by suppressing the competing HER. Test whether the surface area can affect can further enhance the selectivity to acetaldehyde for the copper AG system. A porous CO silver, copper silver nanofluoride electrode was prepared and evaluated for COR similarity. Although a trend in normalized contrast indicates that there are some uncertainties in attempting to translate silver galvanic exchange technique from the planar morphology to the NF morphology. We nevertheless observed substantial additional in most reaction rate and selectivity to acetaldehyde. The Friday efficiency for acetaldehyde production on the C copper, silver, and of electrode reached 70% with an overall of COR reaction rate 3 times greater than that of planar system at an applied potential of only 0 minus 0.33 watt versus RHE representing a 0.2 watt improvement in power potential based on the genomic current density. Thus, these results further validate the concept that high electrosurface area can improve selectivity, not just reaction rate, a principle that can likely extend further to other catalyst material. To conclude all the discussion where we show and represent why we use copper, silver to make acetaldehyde. So it is ordered in summary, copper filtrate controls have been investigated for copper reduction under unplanned conditions. Unprecedented selectivity acetaldehyde was there and low overpotential of planar copper electrodes. The activity study was further improved by increasing the copper electrode surface area. DFT calculation demonstrate that silver atoms can tune the surface binding energy of reduced aldehyde intermediates, resulting in suspension of acetaldehyde reduction to ethanol. This study emphasizes how deliberate modification to catalyst surface area reaction can greatly improve product selectivity, providing a design principle that can be extended to other catalysts and related electrolytic reaction. Then the application of acetaldehyde is given and which instrument first of then we discuss the application of acetaldehyde. First of all, we talk about the instrument we use in the this application: power reflection and Fourier transform infrared spectra were obtained using spectrum 1 FTIR spectrometer, transition electron microscopy. Morphology of the sample was observed and scanning electron microscope. Sensitive method, senses of ZRMOF. It was prepared by following previously reported procedure. Typically, Z-chlorine 4 and 2-amino tetrafolate were dissolved in anhydrous dimethyl formate at room temperature. After that, acetic acid was added in around the obtained mixture was stirred at room temperature about 30 millimeter. That transferred to 30 millimeter Teflon liner and heated at 120 degrees Celsius for 24 hours. After aging, precipitated were collected by centrifugation and washed with N-dimethyl formate ethanol. The product was obtained after drying under vacuum. Then we talk about synthesis of AMC. Briefly, 1 gram of cytosine was dissolved in 50 millimeter of deionized water and the pH of Mixture was adjusted to 10 with 0.1 mole per liter and reversed then 2 ml of acetaldehyde to drop by and the mixture was stirred at a temperature of 4 hours. Then the dark mass consists of ZR AMC was dissolved in 2 ml and then 100 gram of 1 ethyl carbonamide and 100 mg of N-hydrosuccinate introduced for the activation of the carboxyl group in AMC. When an MO of 40 gram added and stirred at room temperature for 8 hours, the product was washed with deionized water and then brown color product was obtained by freezing, drying, and vacuum. Luminescence properties. The fluorescent proportion properties of MO of AMC and ZRMO were measured the excitation wavelength of 380 nanometer and all the samples were kept at same concentration. In order to explore the capability of ZRM over AM0 fluorescence profit determination was added to JSH solution of different concentration. After the mixture has been incubated at 37 degrees Celsius for 3 hours, the fluorescence was measured effect of microenvironment of the cell on the fluorescence was explored. The variation in fluorescence of AMC burns of GS at different concentration at pH 5.8 and pH were investigated. Drug loading and drug release. ZRMO was dispersed in 20 ml of MTX solution and stayed for 24 hours. The substance was then collected and measured by UV spectrophotometry at 300 nanometer to calculate the MTX drug loading efficiency and drug loading control called the following equation. In order to investigate pH, GS, responsive release behavior and TX sample of the loaded or packaged into the analysis bag and then each one immersed in 25 ml PBS solution and given pH and air concentration or different time points 3 ml solution were removed to determine the concentration of MTX and then it was replaced with 3 ml fresh PBS solution. Three independent experiments was carried out for each condition to obtain mean value. In vitro cellular toxicity. All cells were currently provided by the stem cell bank. Chinese Academies of Sciences have G2 and L0 to cell were cultured in standard cell media and chicks were flooded, incubated in 5% CO2 and 37 degrees Celsius for 24 hours. Then different concentration of particle added into 96 well plates. Then cell were cultured for further 24 hours. Cell viability was determined using the CKK8 and 2H tetrazolium monosulfate salt assay. The cell was cultured for 24 hours. That is M over AMC particle in a 96 well plate in a final volume of 200 microliter with 20,000 cells per wall. Well, this cell was then incubated with 100 ml free ZM of AMC in PBS buffer for 24 hours. Server reason 3 times in PBS then 100 milliliter for 100 microliter for 0.1 mg ml minus for CKK8 solution were added to each well and incubated for 30 minutes at 37 degrees Celsius. Finally, a LISA reader was used to measure absorbance at 380 nanometer each well. Result was expressed as the cell availability percentage. Untreated cells in medium were used as control. Intracellular imaging of GSH. In order to further verify the practice of GSH in sociology system, the imaging capability of ZMOF AMC for reduction of intracellular GS was assessed. There cell were cultured in 96 well plates with 1 10 4 cells with per word cell for 24 or on 22 millimeter glass converse slips in the area at 37 degrees Celsius in a 5% CO2 incubator. The culture cell were washed with phosphate buffer and treated with 0.2 mg meter liter per liter ZMOS MC for 3 or control experiment cell were pre-incubated with 500 mole per liter and for 30 minutes to 7 days the house in the cell and then incubated with 0.2 mgml in the culture medium for 3 hours. Finally, the process image of cell treated and treated with NEM was obtained by confocal laser scanning microscopy with X 380 424 814 nanometer. Luminescence properties. The fluorescence spectrum of the was shown. There has a fluorescence peak at 475 nanometer, while the fluorescence peak of AMC is at 500 nanometer. In comparison, the fluorescence intensity of ZM of AMC is visually enhanced, and fluorescence peak is below shifted to 450 nanometer, which can be explained by the intermolecular effect. Now, explore the potential of using the M as a prop for GSS detection. The effect of GS on the fluorescence of ZRMO AMC was investigated. Show that versus intensity significantly increasing with the addition of GSH. This are bond in AMC to expose the glutathione microenvironment and thiol sulfuric exchange reaction occur between thiazide and glutathione, resulting in the cleavage of acids bond into thiols to produce two fluorescent molecule. The fluorescent industry remarkably enhanced as two fluorescent molecule diffuse to prove that the MOS AMC can be used to quantify detect GSS the fact of different concentration of JSH on the fluorescence of ZRM of AMC was examined. With increasing concentration of GSH, the fluorescence intensity gradually increases intensity proportional to the concentration of JSH. Relation between fluorescence intensity and JSH concentration follows the polynomial function. F is equal to -74 E plus 273 within concentration range of 0 to 10 millimeter per liter JSH. A linear calibration curve can be obtained in concentration range of 0.01 m d to the minus 1. The linear equation is F1 and the limit of detection is 4.624 micromole per liter, where sigma is the standard deviation of black measurement and K is slow. The limit of detection is lower than those of most GS detection probes. For the purpose of demonstrating the potential application of ZRF or AMC GS in the cancer cell, where pH value generally varies significantly, the process of ZRMOF was investigated at pH 5.8 and 7.4. As shown, the fluorescence of the ZRMOF depend upon the concentration of GSS, and pH has no effect. This provides good proof of suitability of ZMOF as a probe for detecting the GS concentration in the biological environment. In vitro cytotoxicity. To investigate the cellular microenvironment targeted drug releases under MOF was performed. HAP G2 cells and L02 cells were used to represent cancer cell and normal cell, respectively. The cell variability of F0 cell and L02 cell after incubation were different concentration of Z and MOF are shown. It can be seen from the survival rate of both cell incubated with 150 microgram meter per liter of ZAMC are above 80%, demonstrating a low efficacy and good biocompatibility of AMC. It is worth mentioning that the cell variability of HEC, D2 and L02 are different incubation with the AMC. The survival rate of L02 cell incubated with 300 microgram per meter per liter of AMC is still above 80%, incubating a liter MTX lead and normal. In contrast, survival rate of HPG cell is 76% after incubation with only 25 microgram per meter of AMC and 63% with 200 microgram liter of AMC. As shown, the enhanced cytotoxin HAP-G2 cell of MTX loaded is due to endocytosis mediated intercellular drug delivery through the nanocarrier. This shows that AMC is passively targeted easily in enriched gaseous cell, resulting in greater lesion load in this gaseous cell than in normal cell due to the pH to response of drug carrier and special micromovement of gaseous cell shows reduce something to normal cell, thus will have reduced defects. Then we talk about the uses of acetaldehyde. As acetaldehyde has a broad range of applications, so it has broad range of uses. First of all, are e-cigarettes. A study of aldehyde from e-cigarette in comparison to tobacco cigarette research aimed to replicate a previous study finding a test new generation atomizer under controlled condition. Results show significantly lower level of formaldehyde acetaldehyde compared to the earlier study, especially new atomizer tested. Despite higher aerosol production, a new generation atomizer injected minimal aldehyde. The study emphasized the importance of checking for dry puffs during EC emission testing, suggests that modern ECS when used drastically a minimum aldehyde. Highlight the need of variant method in ECL soil analysis. Additionally, consuming 5 grams a day of EC liquid significantly reduces a novel thiol aldehyde addition. The cross-linked hydrolysis that is produced, these hydrogels exhibit adaptively for easy application on irregular wounds and can transition from semi-solid to solid state, providing suitable elasticity for wound protection. The solution of these hydrolysis treated by thiol, hemi-thioacetal exchange reaction with thiol containing compound like glutathione and cetacine. So it demonstrated the potential of this hydrogen wound management and offering adaptability and control the solution and biocompatibility. They have been tested in scale wound treatment on animals, showing promising results in wound healing and tissue regeneration and minimum inflammatory responses. All other research are promising value for the development of adaptive, easily removable, and biocompatible hydrogen-based wound dressing control will control the solution property, potentially improving wound healing outcomes. Common organic frameworks. The category of crystalline porous organic polymers formed by collecting organic urine through common bonds. These materials have diverse applications such as gas storage, separation, catalyst, sensing, drug delivery, energy storage, photoelectric non-device. These the text details as this the two types of sewers based on amine leaks, which are less common than imine leakage in source. It is highlights the challenges in designing and predicting the structure due to significant structural change from planet tetrahedral during amine formation. The role of cancer stem cell in gynecology cancer, particularly focusing on the resistance to conventional therapy, is significant to targeting LDH, aldehyde dehydrogenase, and the potential strategies to combat CSVS. It's claimed that while surgery, chemotherapy, radiation are the primary treatment, they often fail to eliminate cancer, leading to recurrence, metastasis, and probably causing surviving initial treatment. And then these are the references from which all this content is being taken, and thank you for all this.